Okay, hi, AP Chemistry class. This is your lesson for Tuesday, September 24th, 2019. It's on the subject of limiting reactants. You had an earlier assignment that was titled Limiting Reactants. That was an error because, or simply I deleted that, this from that lesson because I thought it was too much. So this is actually the lesson on limiting reactants. So limiting reactant problems involve situations in which one of the reactants runs out before the other. So if you look at this chemical equation, if I had exactly 2 moles of hydrogen gas and exactly 1 mole of oxygen gas, I'd get exactly 2 moles of water, and there would be nothing left over of the hydrogen and the oxygen. We'd just end up with water. Or if I doubled that, I had 200 moles of hydrogen gas, 100 moles of oxygen, I'd end up with 200 moles of water, but same thing. I wouldn't have any of these left over as long as I had exactly a 2-to-1 ratio of hydrogen to oxygen. But what if it wasn't 2-to-1? What if it was 3 moles of hydrogen for 1 mole of oxygen? Then it turns out that the oxygen would run out before I had used up all of my hydrogen. And typically that's the way it is in the real world. You don't have exactly this ratio, 2-to-1 of this or of anything else that you're doing. So in limiting reactant problems, you are given a number of grams or moles of both reactants. If you're not given the exact ratio of moles of the reactants that are shown in the chemical equation, then one of the reactants will be limiting. It's going to run out first. Okay, so the way to solve limiting reactant problems is to run the reactions twice. Once where you use all of the first reactant and once where you use all of the second reactant. You then determine which of the 2 reactions can actually work with the amount of reactants you were given. So let's look at this example. So this looks familiar. Down here we have grams. I didn't fill this in. And you can have an arrow to the grams from your molar mass. And your molar mass is the translator that gets us into the chemical reaction. And this is the chemical reaction, is what I'm putting the box around. And of course we can do this with all of these. Okay, now one thing that's different from previous reactions is we have 2 rows for moles. Again, anything that's inside the chemical reaction is in moles. Because before we just assumed that we were going to have exactly as much of one reactant as the other. But now we're assuming we don't have that. So what we have to do is say, what if we used up all of the H2? What would the reaction look like? What if we used up all of the O2? What would the reaction look like for a given set of reactants? So here's the example we're going to use. You're given 6 moles of H2 and 4 moles of O2. So what I'm going to do is in the H2 column right here, and where it says all H2, I'm going to use all of the H2 it says we were given, which is 6 moles. And it says we're given 4 moles of O2. So in the O2 column here, and in the row that says all O2, I'm going to assume we have a reaction where we use all of the O2. Okay, now what I have to do is using these, remember these are not an exact number of moles, they're a relationship. I need twice as many moles of H2 as I have of O2, or said the other way, I need half as many moles of O2 as I have moles of H2. So if I have 6 moles of H2 here, I need half as many moles here in order to make this reaction completely take place so that we use up all of the H2 and the O2. So if I have 6 moles here, that means O2 I have to have 3 moles. So 1 to 2, 1 to 2. And now what about here? Again, it's a 1 to 2 relationship. I need twice as many moles of hydrogen here as I have moles of oxygen there. So if this is 4, this has to be twice that many. This is 8. And one thing I ask you to do is when you put the 6 moles in here, since that's an amount that you know you have, it was given to you, circle it. That tells you that that's an absolute correct amount that you know you have to work with. Same with the 4 moles of oxygen. So what we're going to do is we're going to go to each of these boxes and we're going to ask, do we have at least that many moles of that substance? That means at least, the word at least means I have that much or more. So do we have at least 6 moles of H2? Well, yes, we were given 6 moles, so we know we have at least 6 moles. So I'm going to just write the word yes. I would like you to do this, to write these yeses and nos until you really become proficient at this process. Okay, the next one is, do we have at least 3 moles of O2? Well, it said we were given 4 moles of O2, so yes, we have at least 3 moles of O2 to work with. So that's a yes. Do we have at least 4 moles of O2? Well, yes, we just said that we have 4 moles of O2. We were given that. So this is a yes. Finally, the last one here. Do we have at least 8 moles of H2 to work with? The answer is no. We were only given 6 moles. We don't have at least 8 moles, so that's a no. You're going to find out in this process you're going to end up with 3 yeses and a no. If you don't, you did something wrong. Okay, it's always going to be 3 of them are yes and 1 of them is no. So what we're saying is we don't really have 8 moles. We needed twice as many moles of O2 to make this reaction completely run to completion, but we don't have twice as many moles of O2, which is 8 moles. We only have 6 moles. So our limiting reactant is the one in this column. It's H2. So the question is, what is the limiting reactant? I can write that right here. It's H2. What quantity of the excess reactant remains? Well, first of all, let's answer the question, what's the excess reactant? It's the other one. So O2 is our excess reactant. Why? Because it has yes in both of the O2 columns. We have as much O2 as we need to run either of these reactions, either the first reaction or the second. So that's a good one. That's definitely the one that we're going to have left over. That's the excess. But how much? Well, first of all, let's determine which reaction works. This reaction, the bottom one, doesn't work because we don't have enough H2. So we can just lightly, if you want, put a line through this. This reaction does not work. The reaction that's going to work is the one up on the top, the one where we burn all of the H2. And it is, it's not being burned, it's being synthesized into water. Okay, so this is the reaction that works, the one on the top. All right. So that means in this reaction we're going to use 6 moles of H2, that's how much we were given, and 3 moles of O2, but we were given actually more than 3 moles. So how much will we have left over? Well, we were given 4, and we had to use 3, so 4 minus 3 equals 1 mole of O2 is in excess. Okay? Now, how many moles of H2 can be formed by this reaction? And this is really an easy question, but some students are having trouble with it. That's okay. What this is, remember, these are not exact numbers of moles. They're relationships. I need twice as many moles of H2 as O2, whatever number that happens to be. In this case, it's 3 moles of O2. I have twice as many of H2. So you can always relate these by what these numbers are. So if I have 2 moles of H2 and 2 moles of H2O, that means this is a 1-to-1 relationship. You have the same number of moles of H2 as O2. So if in my actual reaction that I'm going to run, this first one, I have 6 moles of H2, I'm going to have the same number of moles of H2O, 6. Again, just simply think of it as these 2 numbers in the equation are the same, so these 2 numbers have to be the same. Another way I could have looked at it is this number is twice this number. So I could have said whatever this number is, I have to double it to get this number. I could have done it either way, but it was just easier to do this relationship here. Okay, so how many moles of H2O can be formed? The answer is 6 moles. And finally, the last question is, how many grams of H2O can be formed? And this is just simply coming from moles out to grams. There's our question mark there. And so we use the molar mass conversion. Let's see if I can fit it in here. So we have 6 moles of H2O times, it's either 18.02 grams of H2O over 1 mole of H2O or 1 mole of H2O over 18.02 grams. I need moles on the bottom, so it's 1 mole H2O. And up on top, it's 18.02 grams of H2O. And we did that in class, and I think that came out to be 108.12, I'm pretty sure. You can check my math on that. But you end up with 108.12 grams of H2O. And so that's how you do a limiting reactant problem. They're not that hard. If you do about 5 of them, you'll be an expert. Okay, they're really not that hard to do. Okay, so let's go ahead and do your assignment. I'm giving you 3 problems. And I'll do the first one a little more slowly, and then I'll do the next two a bit faster. Okay, so here we go. So we got this reaction with silver metal and hydrogen sulfide, and you're going to end up with silver sulfide and hydrogen gas. So let's look at what the question's giving us. It says what we're given. We actually know we have this amount. We start with 6.4 moles of silver. So up here under silver and in the all silver, we're going to assume we use all 6.4 moles of silver. Okay, and I really don't need to write mole. Everything that's inside the dashed line, that's the chemical world, the world of the equation, that's going to be in moles. Okay, it says I have 2.8 moles of H2, so here's 2.8. All right, and now what I want to do is fill in these two boxes. What I'm going to do is see which of these reactions can work and which one can't work, because one of them is going to run out first. One of these two, unless it's a perfect 2-to-1 relationship between these two, one of them is going to run out first. Okay, so what do we need to put here? Well, we see we have twice as much silver as we have hydrogen sulfide. It's a 2-to-1 relationship. So that means this number is twice this number. So if you divide by 2, you get 3.2 moles of hydrogen sulfide. Same thing down here. This number has to be twice this number because of the 2-to-1 relationship. So I take this number and I double it, and I get 5.6. Now, the one thing I did ask you to do is as soon as you write in the amounts that you were given, circle them, because you know that you have the 6.4 moles of silver and the 2.8 moles of H2S. So now what we're going to do is go around to these 4 boxes and determine, do we have at least this many moles of this substance? That means this many or more. Do we have this many or more? So these two are yeses automatically, the ones with the circles. We have at least that much of those two compounds. Now we go over to hydrogen sulfide. Do we have at least 3.2 moles of hydrogen sulfide? And the answer is no. We were only given 2.8. In order to make this reaction run completely so that both of these are used up, we have to have 3.2 moles, but we weren't given 3.2, we were only given 2.8. So the answer to this is no, we don't have at least 3.2 moles. Finally, we can do this box. Do we have at least 5.6 moles of silver? The answer is yes. We were given 6.4 moles, so yes, we do have at least 5.6. Okay, 5.6 or more. We do have more than 5.6. So this is a yes. And you're always going to end up with 3 yeses and a no. So your limiting reactant is the one that's in the column with the no in it. That's the first thing you identify, so we can write that down. Now, I would like you to write complete sentences. I'll write complete sentences too. But what's the limiting reactant? The limiting reactant... Actually, I take that back. I'm not going to always do it. Because I know you want to get through this video, but you should do that. You get in the habit, because that's what the AP exam is going to require. The limiting reactant is the H2S. Now, why is that? Because it's in the column where the no is. The no is in this column. These are 2 yeses over here. Okay, next, what is the excess reactant? That's the other one. It's Ag. Okay. Next question, how much of the excess reactant is left? So first of all, let's identify which reaction is going to work. It's the one in the row. Is it this one or this one? It's the one in the row that has the 2 yeses. So it's the bottom reaction. So I'm just going to put a box around that. That's the reaction that we can actually get to take place. So what it says is that the excess reactant is silver. We have to use 5.6 moles to make this reaction work. But we were given 6.4 moles. We were given more than that. So how much is left over? The answer is the 6.4 that we were given minus the 5.6 that we actually had to use. And that gives us 0.8 moles of silver is in excess. Okay, next question. How many moles of H2 gas is created? So, again, this is not difficult. I just come over here. I want to know how many moles. This is my question mark there. How many moles of H2 gas is created? So I just find a relationship. This is a 1-to-1 relationship. That's the easiest one to use. So if I have 3.2 moles of H2S, if there's the same number of moles of H2 as H2S, if I have 3.2 moles of H2S, That means over here I have 3.2 moles of H2 gas. Just that easy. I could have done it the hard way. I could have said I have 6.4 moles, and I have twice as many moles of Ag as I have of H2 because it's 2 to 1, so I have to divide this by 2, and I get 3.2. Either way gets you to the same answer. So the answer is 3.2 moles of H2 gas. Finally, how many moles of Ag2S is formed? Again, we come over here. It's a 1-to-1 relationship between H2S and AgS. So if it's 3.2 there, it's 3.2 there. So again, notice the relationship. This is the same as this, is the same as this, but this one is twice all of these. This is the same as this, is the same as this, but this one is twice all of these. And that's how that problem works. And so the answer for this one is 3.2 mole of Ag2S. Okay, and that takes care of that problem. Okay, so we're going to go on to the next problem, which deals with this same chemical equation. I did as best I could to erase everything that I had before because we're going to need to start over and use those squares for something else. So let's go over to the other side. And it says you react 7.1 grams of silver with 22.6 grams of H2S. So now you notice things are in grams. So grams is something we would write down here. So we have 7.1 grams of silver, and we have 22.6 grams of hydrogen sulfide. Okay, so now again, the chemical equation inside this dashed line does not speak in the language of grams, so we have to do what we've done many times already. We have to convert from grams into moles. Okay, so we're going to go ahead and do that. So over here on this side, I'll just find some space over here. So 7.1 grams of silver times 1 mole of silver for every, and use your molar mass conversion here, 107.9 grams of silver. And we go ahead and crank that out on our calculator. It's 7.1. Well, first of all, it's canceled. Grams cancels with grams, so the last man standing is moles of silver. Okay, so it's 7.1 divided by, well, 7.1 times 1 divided by 107.9, and we get 0.66 or 0.066. I think in class I may have written that as 0.66, so if I did, you may have to correct your numbers there. It's that many grams, that many moles of silver. Okay, so this is one of our key numbers that we're going to use inside the chemical equation. The next one is 22.6 grams of H2S. I go back over here and I find the molar mass of H2S, which is 34.09. I need grams to cancel out, moles to appear on top, so it's 1 mole of H2S over 34.09 grams of H2S. Okay, grams of H2S cancels and cancels, and we're left with moles of H2S, so we have 22.6 divided by 34.09, and that gives us, oh, there's the 0.66. Wow, look at that, they're almost the same number. And that's moles of H2S. Okay, so these are the two numbers that are circled that we're going to work with. So let's go back to our flow chart. So we have 0.066 moles of silver. So if we used all the silver, we would be using 0.066 moles. These are all moles in here, so I don't need to write moles. And over here, 0.66 of hydrogen sulfide. So we go to the hydrogen sulfide common, and this should be H2S. So correct that, one of the number of corrections on this sheet. So that's going to be 0.66 moles of H2S. All right, so you can circle those because you know you have that much of each of those. All right, so let's go ahead and figure out the relationships here. Okay, so you have twice as much of silver as you have of hydrogen sulfide, because you have a 2 there and a 1 there. Twice as much of this as this. So you have twice as much here as here. So if we divide 0.66 divided by 2, and we get 0.033. Okay, down here we have 6.66, and over here we're going to have twice as much. Again, it's a 2-to-1 relationship. So 0.66 times 2 equals 1.32. And now we have all of our relationships. So now we ask, do we have enough of each of these? Well, the circled ones, the answer is yes. We were given that much, so we know we have that much to work with. Okay, how about this one? Do we have at least 0.033 moles of H2S? Well, yeah, we have a heck of a lot more than that. We have 0.66. So we have at least this much to make this reaction up here work. So the answer is yes on this one. How about down here? Do we have at least 1.32 moles of H2S to make this reaction work? No. We only have 0.066. So we can't make this reaction work. We're going to run out. So this becomes a no. So the column that has the no in it is the one that's the limiting reactant. In that case, it's silver. So we come over here. What is the limiting reactant? It's Ag. Okay. The other one has to be the excess reactant. That's H2S. How many grams of the excess are remaining? Okay, so this one's a couple of steps. First of all, the reaction that's going to work is the one with the 2 yeses in the row here. So I'm going to put a big box around this top reaction. It's the top reaction that will actually work. All right, so we actually used 0.033 moles, but we had 0.66 to work with. So the difference between those is how many moles of H2S we have left over. So it's going to be 0.66 moles of H2S minus 0.033 moles of H2S. And if we do the math on that, we get 0.627. So that's going to be 0.627. I think we maybe got a slightly different number in class. Don't worry about that. We're not going to worry too much about that. But, and that's moles. So this is excess of H2S, which was our excess reactant. Now we need to convert it to grams. It's asking us for grams right here of the excess. So we simply use our molar mass. 1 mole equals 34.02 grams of H2S. So we set it up so that units cancel. And that's going to be 1 mole on the bottom. It's a molar mass. And on the top we have 34.09 grams of H2S. So that'll tell us how many grams of H2S were left over. This is the amount of moles left over, and all we're doing is converting it into grams. So it's 34.09 times 0.627, and that gives us 21.4. So 21.4 grams of H2S are the excess. And don't forget when you compute numbers, what is it you were figuring out? You're figuring out how much of this is excess right there, okay? All right, next. How many grams of Ag2S are formed? So, we have to use the reaction that works. The reaction that works is the top one. We can just lightly put a line through the bottom when we're not going to use this anymore, this sheet. Okay, so very simply, you figure out how many moles of each of these. Just go ahead and do that right now. If there's 1 mole of H2S and 1 mole of Ag2 in the equation, that means it's a 1-to-1 relationship. So if I have 0.033 here, I have 0.033 here. And let's go ahead and just answer the question over here. I also have 0.033 here. Okay, so now we can figure out grams of either of those substances. So it's asking us for the grams of Ag2S. So I have 0.033 moles. There's the molar mass, 247.87. I need grams on top, moles on bottom. So let's go ahead and do that. So it's 0.033 grams of this. And we're converting the, moles of this, I apologize. Moles of that. We're trying to get to grams. And we're going to multiply by 247.87 grams of Ag2S. That's over 1 mole of Ag2S. That's the molar mass. Moles Ag2S cancel the moles Ag2S. And you just do the math on this one. And you should get 8.18. And I'm being really inconsistent with my decimal places, and I'm not even thinking about significant figures here. Grams of Ag2S. That's how much would be produced by this combination of reactants. Okay. All right. How many grams of H2? Same thing, except you do it with H2. So we have 0.033 moles of H2. So it is 0.033 moles of H2, hydrogen gas, times the molar mass. We need to get to grams. So it's 2.02 grams of hydrogen gas for every 1 mole of hydrogen gas. Moles hydrogen gas cancel the moles of hydrogen gas, and you have 2.02 times 0.033, and that gives us 0.067 grams of hydrogen gas. Okay. Sorry, I'm a little off screen there. Okay, anyway, you got that. Okay, and now I threw a little bit of a curveball here and tell you I was going to ask you about liters. I didn't give you any liters. How many liters of hydrogen gas? Well, it's the same number of moles, 0.033 moles of hydrogen gas. Okay, we're going to multiply that by the conversion between moles and liters of any gas. That's what we learned yesterday. So it's 22.4 liters of hydrogen gas for every 1 mole of hydrogen gas. Sometimes you want to know grams, sometimes you want to know liters. Just depends on what the situation in the lab is that you're working with. So moles of H2, and now you multiply 0.033 times 22.4. And I get 0.74. 0.74 liters of hydrogen gas. Okay, and that takes care of that problem set. Okay, now we're moving on to a new equation. This is ethylene combusting with oxygen. This is a combustion reaction, and combustion reactions are a hydrocarbon plus oxygen. You're lighting a match to it, and what you're getting out is CO2 and water. Okay, you'll see a lot of these. Okay, there's an error here, and we corrected this in class, but be sure you have it. This should be C2H4, and the bottom one should be O2. So go ahead and correct those. All right, so now, again, we're doing moles this time, so that makes it a little easier, a few less conversions. So you react 2.9 moles of C2H4. So we look at the C2H4 column, and we're reacting all of that, everything we were given, so all of the C2H4. So that goes here. Okay. Down here, do the same thing with oxygen. We're given 7.4 moles of oxygen. We're in the oxygen column, and this is the row that says we're going to react all of the oxygen. All 7.4 moles is going to get burned. Okay, so there you go. You have those two. I'm going to circle those because that tells me those are known quantities that we were actually given, that we actually have to work with. Now we're going to calculate the other quantities that we would need to make the reactions run fully to completion, so that all of this is used up and all of this is used up. Well, this one says, go ahead and write your coefficients in, by the way, for ones, and please do that. It helps you to realize that there's a numeric relationship there, okay? So this one, whatever's in this box, has to be 3 times whatever's this box. Since this number is 3 times 1, this number is 3 times greater than this number, then this number has to be 3 times greater than this number. And so we did that, and we got 8.7 moles of O2 there. Now down here we go in the opposite direction. This number is going to be 3 times this number, so we have to take this number and divide it by 3. So again, I'm not particular about decimal places. And we get 2.47. All right, so there we go. We have all 4 of the numbers in those positions. So now we put yeses where we know we have enough of the reactant. We have enough of this because it's circled, and enough of this because it's circled. Now how about this one? To make this top reaction run completely, we have to have 8.7 moles of O2. Do we have at least 8.7 moles of O2? The answer is no. We were only given 7.4 moles of O2. We don't have enough O2 to completely react with 2.9 moles of C2H4. So the answer is no for this one. That's your no. Let's just confirm that this one's good. For this reaction, the bottom one to be able to run, we need to have at least 2.47 moles of C2H4. Do we have that? Yeah, we have more than that. We have 2.9 moles of C2H4. So yes, we have enough of this to react completely with this. So this is a yes. So the limiting reactant is going to be oxygen because that's the column that has the no in it. And the reaction that's going to actually be able to work is the bottom one because that's the one that has yeses in both positions here. Yes, yes, that means this reaction runs, this one doesn't. So that's that. So if this is the limiting reactant, then the excess reactant is C2H4. So first question though was, what's the limiting reactant? It's O2. What is the excess reactant? It's the other one. Okay, you write complete sentences, please. Get used to it. How much of the excess is left? So this is the reaction that's actually going to run. Okay, and we had to use 2.47 moles to make this reaction run. But we were given more than that. We were given 2.9 moles. So you just do a subtraction. It's always the bigger minus the smaller. It's not the top minus the bottom. Don't make that mistake. You can't end up with a negative number, which you would in some cases if you did that. So it's 2.9 minus 2.47, and let's just do that, and that gives us 2.9 minus 2.47 and 43. I knew that. Mix it up. 0.43 moles of C2H4 in excess is the way it's usually worded, in excess. Okay, where am I? I'm off the screen. Sorry, guys. That's a simple enough. Okay, 2.9. So this number minus this number gives you that number, and that's the moles of C2H4 in excess. Okay, how many moles of CO2 are created? So let's come on down here. So we have 2 moles of CO2 here. So what's the relationship between that and these numbers up here? Well, 2 to 3 is kind of a quirky relationship. Let's not use that one. Let's use this one. For every 1 mole of C2H4, we have 2 moles of this. In other words, this number needs to be twice this number. So if we have 2.9 here, this number needs to be twice 2.9. So that's going to be 5.8 moles of CO2. Okay, so that answers that. So 5.8 moles of CO2. Down there. Okay, last question. How many moles of H2O is formed? So we come up here, and this one's really easy. There's a 1 there, there's a 1 there, so these two are going to be exactly the same number. So if it's 2.9 there, it's going to be 2.9 there. Okay, and that takes care of the problem number 3. Okay, so for problem number 4, we're going to use the same equation that we just used for 3, but now we're dealing with grams, okay? So we have to do our first thing is get your molar mass conversion done. You got to speak in the language of the chemical equation, which is moles. So 7.1 grams of C2H4. And the molar mass of C2H4 is right here. It's 28.06. I need to get into moles, so the molar mass is 1 mole of C2H4 over 28.06 grams of C2H4. So go ahead and grams of C2H4 cancels, and you end up with moles by dividing 7.1 by 28.06, and it's 0.25. So it's 0.25 moles of C2H4. Now we must have a little more space on these, okay? So that's the number you want to circle, because that's the number you're going to use for the rest of the problem. Next one is, we got to convert O2. So it's 22.6 grams of O2. And I think a lot of you have this one memorized. The molar mass conversion is 1 mole of O2. It's 2 oxygen atoms, so 2 times 16 is 32 grams of O2. Grams of O2 cancels grams of O2, and you have 22.6 divided by 32. And that gives you 0.71 moles of O2. And that's the number you're going to use on the other side. Okay, so I have 0.25 for C2H4 and 0.71 for O2. So I come over here, and in the C2H4 column, all of this, if I used it all, I'd be using 0.25 moles of ethene or ethylene, either one. And down here I got 0.71 moles of O2. Hopefully you can read that clearly over the erasures, okay? So this is what we have. We actually have this much based on our conversion. We know we have that many moles of each of those. So now we do what we did before. We have to have 3 times as much oxygen as C2H4. So this number has to be 3 times 0.25, and that's an easy one to do. It's 0.75. And down here, we have to have 1/3 as much of this as we have this. So if we have 0.71, we have to divide by 3 to get this number. And we get 0.24. We're going to just call it 0.24, 0.24. That's pretty close here, this one. Okay. All right, now we go around and ask, do we have at least this much of each of these? Well, for the givens, the answer is yes. You can automatically put next to those circled ones a yes. Yes and yes. That's hard to read, but that's a yes. So now we ask about this one. Do we have at least 0.75 moles of O2? The answer is no. We were only given 0.71 moles of O2. We don't have enough O2 to actually make this reaction go all the way to completion. So that's a no. So that's a no. How about this? Do we have at least 0.24 moles of C2H4? And yeah, just barely, but we do, because we're actually given 0.25, so we do have enough to make this reaction work. So the bottom reaction is the one that's going to work. The limiting reactant, let me write my yes right there. The limiting reactant is the one with the no in the column. Okay, so we go over, and what is the limiting reactant? It's O2. That's where the no was. How many grams of excess reactant remain? So again, we have to do a calculation. The excess is C2H4. We have 0.25 moles that we were given. We used almost all of it, but not quite. 0.24 moles there. So let's go over there and do the math. So we started with 0.25 moles of C2H4. minus 0.24 moles of C2H4. And that's going to give us 0.01 moles of C2H4. Now we have to convert that to grams. 0.01 moles of C2H4. In other words, this is how much we're going to put back in the jar. We had this left over. We didn't have to use it. So we got a jar of C2H4, which, you don't really, but if you did, you put it back in the jar. So the molar mass, you come back here. This is what gets us out of the chemical equation world, 28.06. So it's 28.06 on the top, grams. On the bottom, it's 1 mole. Moles cancels with moles there, and you end up with 0.01 times 28.06. And those of you that know your math relationships know that if you move the decimal over 2 places, you get your answer. So it's 0.28, and I could write 06. I'm just moving this decimal over 2 places, and that's the answer. Grams of C2H4 is what's left over. Okay? There you go. So you put that back in the jar. Okay, how many grams of CO2 are formed? So we come over here, and we see right here that we need to first figure out moles of CO2. So we look for a relationship that's easy to work with. 2 to 3 is quirky. We don't want to deal with that. But there's twice as many moles of CO2 as there are moles of C2H4. So whatever this number is, we have to double it to get this number. So 0.25 doubled is 0.5. Now we have to go back and do a molar mass conversion. CO2 is 44.01. So I do 0.5 moles of CO2 were created. And the molar mass, we need to end up with grams is what we're looking for. So it's 44.01 grams of CO2 for every 1 mole of CO2. Moles canceled with moles of CO2. And half of 44.01, I'm just going to round it to 22. 22.0. You could say 1. I don't really care. It's grams of CO2. That's how much is going to be formed. Okay, again, it was just half of 44. Okay, that's where I got that. All right. How many grams of water is formed? So we come back over here. We got to figure out how many moles of water. This one's easier. We see there's 1 mole in the chemical equation, and there's 1 mole of C2H4, so these two are going to be the same number, 1 to 1. So if I have 0.25 here, I have 0.25 here. Okay, so there you go. Now you got to get outside of the chemical world and get into our world, so it's 0.25 times the molar mass. You need to end up with grams. So we're going to come down here. 0.25 moles of H2O times 18.02 grams of H2O for every 1 mole of H2O. Okay, and moles cancels with moles, and you end up with 0.25 moles of this. And I'm just going to say that's going to be 4.51, I'm going to say. Give or take a rounding error. 4.51 grams of H2O is how much you're going to produce. Okay? All right. And finally, I give you that liters problem again. How many liters of CO2 gas is formed? So we want liters. It is a gas. It has to be a gas to do this. So CO2, again, we go back to how many moles we ended up producing. We ended up producing 0.5. So we use our liters to moles conversion. So you start off with 0.5 moles of CO2. And you multiply that by 22.4 liters of CO2 divided by 1 mole of CO2 per mole of CO2, moles to liter conversion. And so half of 22.4 is 11.2 liters of CO2 is produced. Okay, just multiply to half times 22.4, and that gives you your answer. Okay. Okay, we got one more problem, actually two more, but from this same problem set. Again, make this correction, which I did not make. The first one, it's all Na used, it's this, and then the second reactant is H2O, so change the H2 to H2O. So again, we're going to run the reaction twice. Once where we use all of the sodium, once where we use all the water, and we're going to see which one of those actually works for us. So let's get started. I'm going to rush through this one a little faster. So we have 11.2 moles of sodium. So you go to the sodium column, and all used, and we're going to use all 11.2 moles there. And oxygen, we were given 14.8 moles. So this is where we use all of the oxygen we were given, 14.8. We circle those because those are what are given. We know we have that much to use. And now we have to find the relationship. Well, these are really easy, aren't they? 2 to 2. So that's going to be 11.2. And 2 to 2 in the other direction. That's going to be 14.8. Should have given you this problem first. Okay. Okay, so there you go. So now we ask, do we have at least that much? So for the givens, yes, we know we have 14.8 of H2O. Did I say O2? I meant H2O. And we have 11.2 of Na. So yes for that, for both of those. Now we got to ask ourselves over here. We're going to run this reaction. Do we have at least 11.2 moles of water? The answer is yeah, we have more than that. We have 14.8 moles of water. So yeah, we have that. That's good. We can run that reaction. And now we come down here. To run this reaction, we have to have, to be able to use up all the water, we have to have 14.8 moles of sodium. Do we have that? No. We only have 11.2 moles of sodium, and we need 14.8 to make this reaction run. So no, the sodium's going to run out. So our limiting reactant in this one is the sodium. All right, next. What is the excess reactant? It's the other guy, H2O. The next one is how much of the excess reactant is left. So H2O is the excess. We were given 14.8, but the reaction that's going to work is the one on top. That's the one that has two yeses. Okay, yes and yes. That's why I want you to write these yeses down. They seem a little silly, but write them down. That has two yeses. So that means this reaction works. The one with the no in it, that reaction doesn't work. So this works. So how much excess? So we were given 14.8 moles, but we only had to use 11.2. So it's 14.8 minus 11.2. And that's going to give us, 3.6 moles of H2O. If I'm saying O2, I'm flipping out here. Okay, it's H2O. If I'm not, then I'm still flipping out because I'm not sure if I am. And then again, the expression you use is in excess. In excess. Okay, there you go. How many moles of NaOH is created? Well, that's another easy one. We're creating the same number of moles of NaOH as either of these two. 2, 2, 2. It's the same relationship. So that's going to make this 11.2. Okay, good for that. And finally, how many moles of H2? So this one is only one for, these are 2, 2, 2, and 1. So you're going to have half as much of this as any of these. Okay, so 11.2 divided by 2 is going to give us 5.6 moles of that, of H2. So 5.6 moles of H2. Okay, and that's all there is to that. Okay, the next one. I'm going to try to get this one done fast. So let's do our molar mass conversion. Let's do them up top. So we got 9.3 grams of Na. There it is right there. Okay, times the molar mass, and that is 22.9 grams per mole for sodium. So we need to get it into moles though. So it's 1 mole, so moles goes on top. And the molar mass of sodium is 22.99. Again, you find that on your periodic table. We used to call it atomic mass, but now we're not interested in atoms. We're interested in moles of atoms or molecules. Okay, so that's going to be 22.9 grams of sodium. So grams of sodium cancels here and here. We end up with moles. So what we need to do is 9.3 divided by 22.9. 0.99. And that's going to give us 0.40. Let me say that again. 0.40. That is correct. I think I had it right the first time. Moles of sodium. Okay, that's important. That's the number we're going to use in the next part of the problem. Next, we have 8.4 grams of water. And we're going to multiply that by the molar mass of water because we need to get in moles of water. And a lot of you have this one memorized by now. So grams of water cancels with grams of water. Okay, so we have 8.4 divided by 18.02. All right, and it's 0.47. I'm going to round it, moles of H2O. And that's what we need to use inside of our chemical equation world. So there you go. So we're going to bring these over here. Okay, and this one is 0.40. And this one is 0.47. All right, so again, it's a 1-to-1 relationship. 2 to 2 is a 1-to-1 relationship. So this is going to be 0.40. Okay, erase these yeses because we don't know that those are yeses at this point. Those are from the last one. Okay, and this one again, a 1-to-1 relationship. So this is 0.47. We circle the ones that we know we have. All right, so next question is, to make this reaction completely run, we need 0.4 moles of water. Do we have 0.4 moles of water? Yeah, we have more than that. We have 0.47 we were given. So this is a yes. Of course, the circled ones are yes. Let's check our last one down here. To make this reaction run, we need 0.47 moles of sodium. Do we have that? No. We were only given 0.4 moles of sodium, and we need 0.47, so this one is the no. There's always going to be one that's a no. So the limiting reactant here is sodium because the no is in the sodium column. The reaction that's going to run is the one that has the 2 yeses. That's the top reaction. Okay, so now we can go ahead and work through. And why don't we just do this for the heck of it? First of all, since the bottom reaction doesn't run, you put an X through these boxes. You're not going to use them. What about up here? Let's go ahead and figure it out. It's just that easy. If this is 2 to 2, then that means that this is 0.40, this is 0.40. We're going to need to figure this out eventually, right? And this is half of any of these things. Any of these is half, so 0.40 would be 0.20. Cut it in half because that number is half of any of these numbers. Okay, so 0.20. So now that speeds us along doing our problem. So let's go over to this side. What's the limiting reactant? The limiting reactant is the one that has the no in its column. That's sodium. Okay, how many grams of the excess reactant remain? So this one we ran with, this one used up, the excess reactant is water. We needed 0.4 moles of water. We were given 0.47, so you subtract. And you get 0.07 moles of H2O. And I'm just going to go ahead and keep on with the problem. It's asking us for grams. So you get this many moles left over. You multiply it by the molar mass, which is 18.02 grams of H2O for every 1 mole of H2O. Moles of H2O cancel, so you have 0.07 times 18.02. And what's that give us? 1.26. or 1.3, I don't care. 1.26 grams of H2O is going to be left over. So you can pour that down the sink or drink it, whatever you want to do. Okay, next. How many grams of NaOH are formed? So same thing. Come over here. So we have 0.4 moles of NaOH. We went ahead and figured that out because we knew we were going to use it sooner or later. And you multiply that by the molar mass of NaOH. That one's kind of easy. So it's 0.40 moles of NaOH. So much for being easy. Moles of NaOH times, there's 40 grams exactly of NaOH per mole. Just add up the sodium plus the oxygen plus the hydrogen masses and you get exactly 40. Moles of NaOH cancels and you get 0.4 times 40, which is going to give you 16 grams of NaOH is produced. Right there. How many grams of H2 is formed? Okay, so we have 0.2 moles of H2. Our molar mass is 2.02 grams per mole. So we have 0.2 moles of H2 times 2.02 grams of H2 for every mole. Moles H2 cancels and cancels. And 0.2 times 2.02 is 0.4. I'm just going to give you some decimal numbers. 0.2 times 2.02. 0.40 is good enough. 0.40 grams of H2 is produced. And that floats off into the atmosphere, or you can light it on fire or do anything you want with it. Okay, there you go. All right. Finally, how many liters of H2? So we know the moles of H2. It's 0.2 moles of H2 from the other side, or from up here, same number of moles, times that relationship, 22.4 liters of H2, or of any gas, for every 1 mole of H2. Okay, so it's 0.2 times 22.4. And that gives us 4.48. So 4.48 liters of H2 is formed. All right, so hopefully these are making sense to you by now. I mean, they won't totally maybe make sense, but you're getting, just learn the process. Here's the way I view it. Don't worry about the theory of why this is working. Just learn the procedure. And all the theory and the insights, they come with time as your brain grows. I mean, literally, I mean that. As your brain grows, as your neurons grow, you'll start to see insights as to why these things work. But at first, just learn the process, the mechanical procedure of getting from start to finish. Okay? Good. We came in under an hour this time, and I'll see you in class tomorrow.